Okay. Yeah. This projection works by mapping the laser beams in the horizontal and vertical directions to a 2D image plane defined by the LiDAR field of view in azimuth and elevation angles. In other words, one can understand the 2D range view projection as a panorama image of LiDAR. The commonly used pixel representations are point height, range, and occupancy. Range view projections can be efficiently processed by 2D convolution and preserve the full range information without a range cutoff as in 3D voxels. However, it is hard to incorporate 3D priors, and range view neighborhoods do not match the true 3D neighborhoods, which makes the 3D learning less straightforward. When a vehicle equipped with multiple LiDAR sensors, it's also more difficult to fuse information across LiDARs. Well, previously introduced representations all discretize the irregular point clouds into a regular 2D or 3D grids. We can also use its raw representations as an unordered set of 3D points, where the 3D coordinates can be used as a point feature. We then applied a point-based neural networks for feature learning. Point set representations avoid the discretization error by preserving the precise point locations, often leading to a better object localization. This drawback of this representation mainly lies on its point-wise feature learning. It creates a significant computation overhead from the irregular memory access and dynamic kernel computation. Computation cost also grows linearly with the points count, which can be a burden when we have multiple LiDAR sensors or aggregate multiple swaps from the past. What's more, multi-scale features are often designed for object detection, and this is realized by the key point sampling if we use this point-wise feature learning. However, the different key point sampling strategies can affect the final performance. So, because of the dramatically varying point density of the LiDAR data. To benefit from different representations, we can also fuse features from multiple views together. Feature fusion from multiple views provides a more comprehensive understanding of the data and enabling efficient multi-scale feature learning while preserve the raw points geometry details. But we need to keep in mind that fusing different representations can increase the computation cost as well, as we need to use multiple network branches to process them individually. As we know that 3D voxels and bird's eye view projections are sparse, a natural question arises: can we exploit the data sparsity to speed up computation? The answer is yes. We can utilize the specially designed sparse convolutions to prevent the wasted computation on the empty locations. Sparse convolution works by doing the computation on valid location only, so that the sparsity pattern doesn't change as we stack more convolution layers. And the valid convolution is realized via the image-to-column algorithms. So these sparse convolutions can generate as well, and the speed up can be limited by the number of empty voxels growth, as the image-to-column algorithm is not as fast as a well-optimized dense 2D convolution kernel. Alternatively, we can use a transformer architecture for these feature extractions on the sparse voxels. More recent work, voxel transformer, we can use self-attentions on these sparse voxels. It uses a GPU-based hash table to store non-empty voxels indexes and performs self-attention by searching the non-empty indexes with an attention pattern. So this is more flexible than the sparse convolutions, with attention patterns adapting to sparsity and enabling larger restricted fields. However, compared to the sparse convolution, if we use more voxels in the self-attention computations, it can sometimes be memory consuming. So far, we have discussed various point cloud representations and how to build efficient feature extractors on top. Now we'll briefly discuss different designs for the detection framework. There are two major object detection frameworks, which are one-stage and two-stage. While one-stage detectors produce pixel-wise object estimations from a single forward pass through the model backbone and header, two-stage detectors decompose the task into two steps. First, we generate the object proposal densely, and then refine the proposals based on the region-specific features. We first review the one-stage detectors, which produce dense 3D output in terms of box estimation and class probabilities from a last layers feature of the backbone. For 3D estimation, 3D box estimation, we can either directly regress the 3D size and orientation of a bounding box at each pixel of the output feature map. Alternatively, we can result a set of predefined anchors. For each output pixel, the model predicts the probabilities for every anchor, as well as the residual information with respect to the anchor shape. As a result, the issue of large object shape variance can be elevated to some extent. One-stage detectors typically have real-time inference speed and fewer hyperparameters to tune in general. However, they may suffer from imprecise object localization, as in many cases, we are estimating the object boundary from a center pixel alone. In contrast, two-stage 3D object detectors introduce region feature pooling to further refine the initial object refinement. The first stage is similar to a one-stage detector, and the second stage takes a high confidence first stage detection and extract the region features for box refinement. In practice, we can add more stages afterwards to further refine the detection. The popular detail-like model with multiple transformer decoder layers as a header can also be categorized as two-stage in this context. Two-stage detectors can achieve state-of-the-art detection accuracy, but at the cost of slower inference and more hyperparameters than one-stage detectors. Next, we'll discuss camera-based approaches for 3D perception. So cameras are appealing in that they are much cheaper than LiDAR, provide textual information and capture fine details. However, they lose the depth information, which is important for 3D perception. In order to reason about 3D from the 2D image space, we need to lift the information from 2D to 3D space to help the model further produce the 3D bounding box which we required. This lift can happen either at input or feature or the output stage. Yeah, we first look at the method that lifted the 3D as output level, which directly predicts the 3D bounding boxes from the 2D pixel features. To bridge the gap between the 2D features and the 3D targets, several techniques have been proposed. From the perspective of feature learning, we can add a 3D LiDAR data as input during training and regularize the 2D image features to match the 3D LiDAR features, and then remove the LiDAR as a test time. From the perspective of output parameterization, instead of directly predict the 3D box, we can predict the object key points in 2D and solve the 3D bounding box via template matching, as we show in this figure. This type of approaches can be considered as a simple extension of the existing 2D detectors with a different output target. However, the performance is usually unsatisfactory when measured in 3D space. Now we look at the methods that lift the 3D as an input level, which we also know as a pseudo LiDAR. The first estimates the per pixel depth and convert the image pixels with estimate depth to 3D, following the camera parameters. And we use an off-the-shelf LiDAR-based 3D detector to process the pseudo LiDAR points curve. The depth can be inferred from the monocular camera or stereo camera, or via self-superposition from multiple calibrated camera or even video sequences. Pseudo-LiDAR-based approaches can achieve good results in camera-based 3D perception, but it requires an additional depth model. Instead of lifting to 3D at either input or output level, we can alternatively lift to 3D as a feature level in order to achieve a better trade-off between the exploration and the computation. Specifically, we can first use a 2D CompNet to the camera images to extract the 2D camera feature map. The pixels in the 2D feature maps are then be converted to a 3D space as a 3D points or array via the different mechanism. For example, we can estimate the discrete depth distribution and aggregate the camera features on the PV space. If we have the stereo camera, We can use stir matchings to solve the 2D to 3D ambiguity and further project the 2D features to 3D. And the reason works, which is called BEV former, that use deformer attentions to effectively query the camera features and fuse them in the BEV space. After this feature map transformation, the resulting 3D feature maps is then used to output the 3D detections. Since the features lies in the 3D space, they typically produce a better 3D geometry. Another advantage is that the 2D to 3D feature transformation only requires the camera parameters and can work even without the depth estimation. However, if the depth is unknown, the one-to-many mapping brings ambiguities in the resulting 3D features. Errors in the depth estimation would also lead to misaligned 3D features. So far, we've gone through the perception algorithm that relies on either LiDAR or cameras. Now we'll see how can we combine the LiDAR and cameras together for a more robust perception. Broadly speaking, there are two main pipelines for LiDAR and camera fusions, the cascade pipeline and the parallel pipeline. For parallel pipeline, we further compare the fusion mechanism at different levels. For the cascade fusion approaches, a two-stage model is built. The first stage, we will produce 2D detections from the camera and convert them into 3D frustum using cameras and LiDAR calibration. The second stage will then perform the 3D object localization, giving the LiDAR points within each frustum. This approach can take advantage of mature 2D detectors, which provide high-quality object proposals. Also, in the 3D space, the model only needs to solve the localization task instead of the joint recognition and localization. However, errors in the first stage cannot be recovered, and the 3D localization of the occluded objects within this frustum is difficult. We now take a look at one more widely used parallel pipeline. We first review the output fusion, which is adopted by many systems in industry. In these approaches, the 3D perception runs on each sensor modalities individually, and their perception results are fused together at the tracking level. So the output fusion methods embody the spirits of modular design, and therefore achieve a redundancy of safety. However, each object estimate is typically more unreliable, as it comes from the single sensor, and the rule-based fusion is also error-prone. In contrast to output fusion, input fusion combines the information at the raw sensory data level by converting different sensor modalities into a unified feature space, for example, the 3D space for LiDAR and camera fusion. To find a one-to-one mapping between LiDAR and the image pixels, we project each LiDAR points onto the image plane. If the points fill in within the image and then the corresponding pixels is matched with the LiDAR points, otherwise the LiDAR points has no match. And then we can append the pixel feature like RGB or the semantic labels we predict or the 2D backbone features to associate with the LiDAR points. The enhanced LiDAR point cloud is then fed into an off-the-shelf LiDAR-based detector. Compared with output fusion, input fusion provides a denser raw data fusion. However, it doesn't fully exploit the camera information as it's represented in a primitive low-dimensional format. It is also sensitive to calibration error between the camera and LiDAR. A more promising direction is feature-level fusion, either at coarse ROI-wise or dense pixel-wise. For ROI fusion, we will project the same object ROI to 2D and 3D respectively and combine their feature together. This is usually performed as an ROI pooling layer with a two-stage object detection framework. For pixel-wise fusion, the most straightforward implementation is to fuse pixel and point features by projecting LiDAR points onto the image plane. However, since the LiDAR points are sparse in 3D, and only occupied locations have gathered complementary information from the camera image. This can be addressed with a dense camera to BEV view transformation via deformer attention or discrete depth estimation. After feature interpolation, we can achieve a dense pixel to voxel fusion. like this. Feature-level fusion fully exploits complementary multi-scale information and enabling more robust to small calibration errors. However, it requires a feature extraction on each sensor modalities, which brings more computation cost. In self-driving, there are also a lot of prior knowledge that we can use to improve the system robustness. One such example is high-definition maps. This HD map provides 3D environment geometry and the roadmap semantics. In terms of 3D geometry, many works exploit the ground surface geometry for more robust perception on the hilly road. Specifically, the height of each 3D point is subtracted by the height of the ground so that it becomes invariant to the road slope. We can either build a map offline and query it online, or directly estimate the ground geometry online with the RANSAC or neural networks. HDMap also contains rich semantic information about the road map. One representation for this type of information is raster image, which will rasterize the vector shapes of the road elements as well as the active trajectories, and use different colors to encode different semantic meanings, such as line types, orientations, or motion. We can use a 2D CNN to learn map-specific features, which are later then fused with sensor feature maps for more accurate detection. The raster representations of HDMap is easy to implement and extend. However, they suffer from lossy rendering and limited receptive field and intensive computation. A more intuitive and native representation is lane graph, where we preserve the original vector format of lanes as well as the trajectories. We can use graph neural networks to obtain polyline level feature and model interactions between lanes and agents. The lane graph representations does not lose information, and it can capture larger structured receptive field and is more parameter efficient in feature learning. However, it requires a careful design of node and edge features to fully capture the semantic information from the HD map. So far, we have give a brief summary of many building blocks of our perception algorithms. We first talk about the techniques that perform 3D perception from LiDAR and discuss different input representations and detection frameworks. We then review methods that perform 3D perception from the camera sensors. Afterwards, we discuss the different sensor fusion technology strategies that utilize LiDAR camera and map informations. Next, we'll discuss some more advanced topics, including unknown object recognition and other output representations and latency-aware models. We have seen algorithms that focus on a few predefined categories of interest. However, the ability to recognize unknown objects is critical for self-driving. For example, sometimes we can see a deer on the road. Yeah, as we show here. One way to address this challenge is to explain every point in the LiDAR point cloud. In particular, our goal is to identify everything in the scene and classify them as either known or unknown, and recognize the stuff as well, like the road or the building or something. Yeah. One approach to tackle this task is as is shown in this figure below. The main idea behind this model is to project the LiDAR points into a category-agnostic embedding space. Within this embedding space, we can group the points into both known and unknown things and stuff, irrespective to their semantics. Moreover, we could ask a more general question. Can we discover class-agnostic bounding boxes from the raw LiDAR sequences without human annotation? In our recent work, we develop an unsupervised object detector that learns from a sequence of LiDAR point clouds without human supervision. The goal is to identify any object of interest in the given LiDAR sweeps. We first cluster near-range points to produce an initial pseudo-label and utilize CNN's translation equivariance to obtain a long-range pseudo-labels as well. Given pseudo-labels of full range, we utilize an unsupervised offline tracker to find the object tracks and apply trajectory level refinements to ensure that every object has the same physical object size across time. So after a number of self-training runs, we can get our final unsupervised object detector. We've discussed the perception model using 3D or BV bounding boxes as output representations. Reasoning about parametric outputs has an advantage of better interpretability, and the output space itself is low-dimensional. However, in many cases, it also requires additional post-processing like score thresholding and NMS. Through this post-processing, it becomes hard for the downstream model like prediction to fully capture the uncertainty of each object estimates. And sometimes the box is not the best way to describe freeform objects. In the meantime, there are methods that choose to reason about non-parametric outputs like probabilistic occupancy map in 3D or BV, enabling end-to-end learning and uncertainty propagation, but with a higher dimensional and less interpretable outputs. So we'll briefly discuss two recent works that adopt non-parametric output representation. The recent work Lift Splashdot learns BV features from the RGB camera and output objects and map segmentation mask in BV as a perception output. In addition, their model performs motion planning by sampling trajectories on a joint learned BV cost map. Recently, the 3D occupancy prediction has gained people's attention. So the input can be RGB images from the surrounding monocular cameras or sparse LiDAR point clouds. And the expected model output is a much denser occupancy prediction for 3D voxels. The occupancy predictions may contain semantic information with a fine-grained class definition, or could simply be occupied, non-occupied binary classification. This is also known as semantic sync completion task in the semantic kitty benchmark, and is promoted by Tesla with their occupancy network. Instead of producing bounding boxes or segmenting observed LiDAR point clouds, by predicting if each 3D voxel is occupied or not, we can better capture the uncertainty with fine-grained information and handle unknown objects that doesn't belong to our training class definition for safety. So far, we've discussed achieving good accuracy and speed in designing a perception system for self-driving vehicles. When applied in a real-world application, the latency also matters, where the system has little time to wait for the results. So here we show an example of how latency affects our perception system in practice. So where the system is not getting the real-time state estimates of the detected actors. So once we get the results, our vehicles already moved to another place. This video shows the effect of latency in real-world systems. While the model produces accurate outputs for each image, the time it takes to do so introduces latency. And by the time these outputs are ready, they no longer represent the real state of the world. Another work, StarOp, minimizes this LiDAR perception latency by ingesting packets and emitting the stream of detections. So by leveraging a special memory and efficient operators, this model produces accurate detection while achieving latencies 6 times lower than the fast full-sweep detectors. So we use this backbone to operate at the packet level for efficiency, and therefore minimize the data building latency. So the detectors will produce the output for each packet instead of waiting for the full sweep of the LiDAR. Because each LiDAR packet only provides a fragment observation, and we use iteratively updated latent spatial memory to achieve the global context for the better detector results. And furthermore, to quantify the advantage of operating at the packet level, we propose a latency-aware detection matrix. As opposed to the typical mean average position, the green box defines the ground truth instead of the gray. So by doing so, the matrix takes into account the data buffering time in order to estimate the quality of the detector. And the StarOp perform significantly better on these metrics compared with traditional detectors that is not aware of the model latency. So this brings us to the end of this session. To summarize, we discussed how to build a robust 3D perception system by exploiting information from different sources with different sensor fusion strategies. We also talk about unknown object recognition problem and different output representations that have been used for perception. Lastly, we discussed the system latency when we deploy the perception system in the real world. And we want to emphasize that there are many aspects of perceptions for the self-driving that were not covered due to the time limitations. For example, perception from other sensors like radar or ultrasonics and many more. Yeah. Thanks for listening.